Hello, everybody. Good morning, good evening, wherever you are in the world. I hope you're as excited to be here as we all are. So, I am Rachel Rayner. I'm in the marketing team at Bluebotics, which is part of the Zappy group of companies. And I'm really excited to welcome you all to this session. Please remember that this session is also being recorded, which means it will be available to watch on demand following this session. If you've got any questions at all, please add them to the Q&A. You can find that tab to the right of your screen now. Note that all questions will be sent privately, but would like to answer them publicly if we may. With that, I'd love to introduce our speaker. So welcome to Alexandros Mavronas, who is a systems applications engineer at Infineon. We're speaking today about wide-bandgap technologies, which of course are the enablers for compact and efficient electrified systems. So welcome again, Alexandros. Please take it away.
Thank you also for the quick introduction. So as mentioned, I'm Alexandros. I'm a system application engineer at Infineon Technologies based in Munich, Germany. And today I'm going to be presenting to you a wide-bandgap technologies and specifically how they enable compact and efficient electrified systems. Now, just as a quick company introduction, I'm sure you're also, a majority of you are already aware of us. So Infineon is the number one when it comes to the automotive semiconductors, as well as the power discretes and modules, which is also the relevant topic that we're going to be touching today. The main growth areas for us and the main focus applications are the ones that are related to the energy, of course, mobility, as well as IoT. And as a company, we are around 58,000 employees worldwide. We have 71 R&D locations, as well as 15 manufacturing locations all around the world. Now, to the agenda for today, what we're going to cover, we see here in the first session, I'm going to give to you a slight introduction when it comes to silicon versus silicon carbide versus gallium nitride technologies and what are the market trends that we see today. And on the second portion of the presentation, we're going to see and dive a bit deeper into how wide bandgap technologies really enable specific applications and also make them more efficient, but also more compact. And in this case, we're going to touch some specific applications like low voltage motor drives, industrial and EV battery charging, as well as automotive onboard charger, DC-DC and inverter applications. Last but not least, we're going to have a summary here and conclusion of what we presented today, just to close it off, and also then a call to action for the audience. Now, starting with the introduction of silicon versus silicon carbide versus GaN. First of all, I would like to touch a bit here the definition of the wide bandgap technologies. So what we see here basically, and I will not go into too much in depth, in the semiconductor materials, we have two bands known as the valence and the conduction band. And what we call band gap basically is the energy gap that we need to provide basically to the electrons that are attached to the atoms in the so-called valence band and move them into the conduction band where basically they're free to flow and can conduct then electricity. What we see here now is a table with all the different materials that we're going to cover today. So silicon, silicon carbide, and gallium nitride. And seeing here from the table, we can understand why silicon carbide and gallium nitride are called wide bandgap technologies, right? Because the wide bandgap energy is around three times the one of silicon. And this is also how the wide bandgap naming derived. Some other parameters that we see here is, for example, the breakdown field. And here to mention that there is a direct correlation actually between the bandgap energy and the breakdown field of the material. And in this case, we see also that the silicon carbide as well as the gallium nitride is higher than the one of the silicon. Some other parameters that also important and different between the materials are, for example, the electron mobility, so how fast really can the electrons move while conducting electricity, as well as then the thermal conductivity of the different materials. Maybe also to explain here that I have put some ranges in some of this table just because there are some example values, and this really may differ based on the material properties, the device structure, but also the fabrication processes that may be used from different manufacturers. Now, from this table, what we can understand is that we can achieve actually with a wide bandgap higher voltage operation. We can achieve thinner active layers, as well as higher switching frequency because of the electromobility, and also improved heat dissipation because of the thermal conductivity. And what this allows us as well is then to have an extended power density as well as an improved efficiency in our designs. Now, to show a bit of the market that we have today, we try to segment a bit into the different applications that we're seeing. And here you can see on the vertical axis, we have plotted the switching frequency of the different applications. As well on the vertical axis, we have the power related to such applications. And what we see is that actually silicon is not a surprise, can cover really the majority of these applications, and is also very much widely used, targeting 25 volts up to 6.5 kilovolt applications. Now we have the silicon carbide that is, of course, overlapping in some of these applications with the silicon, but also enables some applications which require slightly higher switching frequency, whereas being also high in power. And here the silicon carbide can also cover applications for 400 volts up to 3.3 kilovolts. When it comes to the gallium nitride, what we see is that, again, here there is overlap, of course, with the silicon carbide and silicon in some of the applications. But also here we enable some applications in the higher switching frequency. And also here we target voltage classes going from 40 volts up to 650 volts. Now, to see a bit of the market situation today and what is the market growth that we expect to have. So starting with silicon, of course, this doesn't come as a surprise. This is the mainly used technology today in the market, and also it's bound to growth in the future because of more applications still needing silicon superjunction MOSFETs. From the other side, we have the silicon carbide that at the moment has a relatively smaller, of course, market size because it's a newer technology, but also the predicted growth in the future in a lot of application is higher than the one of silicon. Last but not least, we have the gallium nitride technology, which has an even smaller, I would say, market size today than the one of silicon carbide, but also the expected growth in the future is slightly also higher because of the application it can cover and the unique benefit it has versus silicon carbide, but also versus silicon itself. Now, another topic that we need to understand really is that wide bandgap adoption is heavily dependent also on the end applications. And I think this is a key point that we need to highlight. So I have an example here. We see that for applications like power tools, for example, or railway related applications, silicon is still the technology that we foresee to have in the future, especially due to its best cost to performance in these categories. Silicon carbide, on the other hand, can enable more efficient topologies, for example, when it comes to EV charging, also to energy storage systems. And this is also some applications that we see the higher power capability and also the higher power density of SiC playing a key role also in the future. Last but not least, again, GaN has also its sort of application focus. Like, for example, we see more and more in the onboard charging today in the automotive arena, as well as consumer chargers and servers that really can take advantage of the GaN material capabilities and also the higher efficiency that we can get out of this with the higher switching frequencies. So out of this is really important to understand that each technology will have also in the future its own key applications behind. Now, to try also a bit to, I would say, categorize the different properties of the different materials, we see here the spider chart, and I will not go also into depth with this, but I think just to mention that the key parameters, I would say, what we see is, of course, the temperature, the voltage class, the switching losses, and here the integration as well as the cost of the different materials. And each one of these, I'll take an example, the GaN will be more prominent when it comes to the switching loss and integration. So they will give more benefits when it comes to these parameters. But on the other hand, the silicon carbide, we see that for higher temperature and also designs in harsher environments may give here an edge over the other two technologies. So this was a bit of an introduction to the different technologies. Now we're also really going to go a bit deeper into the different applications that we are seeing. As a real introduction, here we have a nice picture of what we would see, let's say, as a modern city, having the different applications behind. And here I take an example. We see the railways, we see the EV charging in this case, or also we see, for example, like the electric vehicles, as well as solar applications. And what we try to do is to really map the different technologies, so gallium nitride and silicon carbide, where we see the main benefits in the different applications. Out of this, as I mentioned, we're going to start with the low voltage motor drives and then move into the other two applications of focus for today. Starting with this, what do we mean by low voltage motor drives here? And I have some examples, like in this case, robotics, we can see here in the photos, drones, or also light electric vehicles, as for example, e-scooters, but also e-bikes. And in this case, you see also some boards here, which are some designs that we also as Infineon had developed to really showcase how with the medium voltage GaN technology, in this case, we can enable miniaturized designs while also being able to push a lot of power, so ranging basically for a few hundred watts up to 20 kilowatts in this case. How is this now enabled basically from the technology side? So to understand here, we're covering as an example the medium voltage GaN, so 100, for example, voltage class devices. And the unique properties of GaN, as we can see here, basically is that it has as a technology basically no reverse recovery, and without, of course, also no reverse recovery charge. And also the gate charge, or also the charge related to the output capacitance, are lower than silicon MOSFETs in this case. What does this mean for our design? We can go lower into the switching losses by also while going higher in the switching frequency that we have. And what does this give us as well? As you can see here, and we also are going to dive a bit deeper into in the next slide, we can move basically from a design, a field-oriented control in this case, we're going from 20 kilohertz up to 100 kilohertz. We can see how the phase current is changing, especially related to the ripple that we have here. What does this mean for the final application is that we can have a higher power density in this case. The lower current ripple will also help with the motor efficiency that we're going to have. And also we're going to have lower acoustic noise with a higher switching frequency, as well as better motor control dynamics. To go now a bit more in depth, as I shown before this waveform. So in this case, we have a test condition with a 48 volt platform around 300 watts. And we're starting here basically with a switching frequency of 20 kilohertz. What we see moving into a switching frequency of 100 kilohertz is that, first of all, we see that the motor current ripple, as we can see, is going down 5 times. And of course, with that, the motor is becoming more efficient, and we can run basically the motor 13 degrees cooler. Out of this, what we can understand, the motor loss will go, of course, down. The inverter loss here will go a bit up because, of course, here we're switching faster. So the inverter and the switching losses are going to be faster. But our overall system loss then will take a benefit out of this. And I think this is very important. We see here that overall system efficiency will move from 89% to a 96%. Another key aspect of the GaN, as we can see here, is the miniaturization aspect. So using conventional silicon MOSFETs, as we can see, we have this bulk capacitance that is today using electrolytic capacitance that is basically defined by the RMS capability that we need our bus capacitance to have for our application. Moving now to cool GaN based solution, what you see here on the right, is that we can actually replace these electrolytic capacitors with ceramic capacitors, which are always also very, very small. And this also leads to a smaller design when it comes to cool GaN. This also, of course, allowed that the capacitance now on a cool GaN-based system will be defined by the voltage ripple and not anymore by the RMS current, because also the ceramic capacitors have very good RMS capability. So we covered now the low voltage motor drives, and we're going to move now in another application, which is the industrial and EV battery charging. Here, I have as a very introduction slide, sort of generic topology, how it would look like in such an application. So we start here, of course, with the AC grid input, following some rectifiers and also some EMI filters. Usually we have our power factor correction stage, and then together, of course, with a DC-DC stage here to end up with a charging profile, basically depending on which battery we're going to connect into our battery charger. What is also key importance to this application, but also to all other applications, is also to understand the sub-segments that are behind the specific categories. So I take an example here. We need to understand that the forklift, for example, will have a different requirements when it comes to battery charging versus the autonomous guided vehicles. And these requirements are usually, as an example, related to the battery voltages that these systems are using, as well as how fast they need to charge, also related to the power capability that our charger need to have. So it's also very much important to segment this application and really to have an optimized solution for each of these subsegments. To give now an example of how wide-bandgap enables such topologies, here I have the example of a totem pole topology, which can really enable, as we can see, an efficiency of up to 90 or more than 99% at 50% load. And this, as you may know, is only possible because we can enable the fast switching leg of this of the graph that you see here on the right by using wide-bandgap devices like silicon carbide and gallium nitride. Moving now to the EV charging, which is also an adjacent, I would say, application, we need again here to segment between the different requirements that we have. And what we see here on the left is basically an AC charging, where you would, for example, find the wall box in your on your home, which is then connected to the onboard charger of the car itself, and then in series to the BMS and the battery of the vehicle. Another way to do this is, of course, here, as you may know, to use the DC charging capability. So also, for example, the ones that you would find on the highway, that this basically charges directly through the BMS into the battery of the vehicle. And the main difference is that on the right, we can have a faster charging and a higher power output versus the left side. Again here, as we also mentioned for the battery charging before, we need to understand the different subsegments behind these categories. And we have, for example, as I mentioned, the AC wall box when it comes to the residential application, up to a commercial high power chargers. And we see here that we can range from 7 basically kilowatt in the first case up to 50 kilowatts or even more in the latter case. Of course, with that, we need to understand that the solutions that we need to provide and suggest to the customers, and also the power behind. So even it's going to be a discrete solution or a module solution, plays a key role based on the specific application requirements. Now, to showcase some topologies as well for the EV charging, we start here with the PFC. Um, in this case, if a unidirectional charging is needed, I think a lot of you are already aware of the Vienna rectifier. And we see here is a very known topology in the markets, also efficiencies up to 97.5% in this case. And what we're using today is a cool-SiC diodes, as we can see here in the design, in the vertical leg, as well as in the horizontal leg, silicon MOSFET devices. However, what comes into play here when it comes to GaN is the newest technology that's called GaN bidirectional switch. And what we can do with this technology basically is we can replace now these two silicon based switches with just one GaN bidirectional device. And I think this is also a key aspect of how GaN can enable here the miniaturization and the power density of such designs. Some other topologies now, when it comes to bidirectionality, we have the very well-known B6, and this one is also enabled by using 1200 volt silicon carbide devices here. And also on the right, what we can go into more complex, basically topologies, using all three technologies in this case. So in the vertical leg, we can still use silicon-derived technology like IGBTs, or in the horizontal leg, we need to use cool GaN and cool SiC devices. And what these topologies allow us to do is to really increment the efficiency of our design in case this is needed from the application. Moving now to the DC-DC portion for EV charging. What we see here for unidirectional charging is usually a full bridge LLC, and in this case, a lot of times the cascaded approach to be able to support wide output range in the secondary side. This is quite common, I would say, also today in the market. And what we can see is that we can use cool silicon carbide devices instead of silicon-based devices to really here improve the efficiency of this topology. When it comes to bidirectional topologies, the most also prominent today in the market are the dual active bridge, as we can see here on the top, either for a single phase or for a three-phase approach, where again here gallium nitride and silicon carbide play a major role into implementing these topologies. Or as we can see also on the bottom, topologies like CLLC, where also here the peak efficiency is quite high, and also the silicon carbide and gallium nitride with a unique materials can enable higher efficiency when it comes to this topology. So I think also from the slide, it's quite clear from the coloring that these topologies are really, let's say, taking a benefit and being enabled by wide-bandgap technologies. So we discussed so far a lot about efficiency improvement. By why is this efficiency improvement so important, right, for the actual application? So we took here a basic example with some specific assumptions behind, and what we derived basically is that, as we can see, with only a 2% efficiency improvement when it comes to the EV charging, it can allow us for a very significant energy saving, which also then, of course, allows us for a very significant CO2 reduction. This is one aspect. The other aspect that we can also have a look at is that with the same energy, we would be able to charge more cars by basically around 200,000 cars for every 10 million on the road. So I think we can understand that the 2% efficiency when it comes to charging can really help us when it comes also to decarbonization as well as energy saving. Now, moving to the last segment for today. So for the automotive related applications like onboard charger, high voltage to low voltage DC-DC, and inverters, what we see here is a basically mapping of a modern electric car. So now we're going to touch mainly the onboard charger, which, as we also can understand, has a very high efficiency and reduced size requirements. As in the previous applications, what we are trying to do also as Infineon, we are trying to really understand the trends and the requirements of such applications. And in this case, for the onboard charging, what we see is that we need to allow for performance, so power up to 22 kilowatt, as well as having a very high power density, because now the onboard charger is actually sitting in the car, so we can understand that also its weight and also the size plays a major role. Another topic, of course, here is, as in all designs, the efficiency, but also the bidirectionality, for example, to allow for vehicle to grid or vehicle to vehicle charging is a very key aspect of this application. Of course, also here we need to be able to support both 400 and 800 volt battery systems. Together with that, we should also not forget the cost. So we need to balance basically these requirements with the cost. And how is this done is to really find an optimized solution when it comes to the system design. And this optimization can come either from the technology, as we can see, from the packaging that comes together with the technology, but also with the relevant innovation when it comes to the technologies, the topologies that we are using in such system designs. Here I have an example for GaN, and also to mention that the onboard charging has very also similar topologies to the ones that we have seen before in the EV charging as well. So in this case, it's just an example of how GaN can enable in both PFC but also DC stage with its unique benefits. And what we see here on the left, we can see that GaN has as mentioned, also for the low voltage, also for the high voltage, in this case GaN, we have zero reverse recovery, and with that also zero reverse recovery charge. In this case, we can have higher efficiency, of course, and also lower EMI noise. Another key aspect that we see also versus silicon carbide is the temperature dependency of the reverse recovery related charges, but also of the output capacitance related charges. And this we can see also here that the output dependency is really, let's say, excellent when it comes to the GaN technology. Another aspect, as we see here on the right as well for the DC-DC stage, is that the GaN has, in this case, the lowest output capacitance. And also from this graph, what we can see is the output capacitance charge. And another aspect is the linearity of this charge. And what does this allow us is, of course, to also improve EMI, because we have less abrupt, basically, changes during the transits of the MOSFETs. Another topic as well is that we see here the purple, which is the silicon superjunction MOSFET versus the silicon carbide and the gallium nitride, is way higher also when it comes to the value of this charge. This means, of course, as we can see here, that we can achieve lower switching losses, but also smaller magnetics and easier zero voltage switching conditions for such, for soft switching, for example, DC-DC applications. Another aspect of the wide-bandgap, of course, so we have seen some, I would say, quite used topologies, but it's not to be forgotten that also these technologies can allow for more innovative topologies in the future. So what we see on the bottom are some examples, like a three-phase multi-level flying capacitor plus CLLC, or a three-phase single-stage phase modular, or a three-phase single-stage matrix converter on the bottom right. And what you see also from these topologies and also from the coloring that we have used is that really they are enabled by the use of 650 volt GaN, either standalone switches or bidirectional GaN, as well as silicon carbide MOSFETs, in this case, mostly 1200 volt silicon carbide. So I think is also this slide is showing the importance of having these technologies to work with to also innovate when it comes to different topologies. Now, moving to the high voltage to low voltage DC-DC portion of the automotive application. Again, here, of course, we're talking about the DC-DC stage. So there are going to be some similarities in the topologies as the one that we have seen before, also, for example, for EV charging. Just take an example as well here for a GaN solution for 400 volt batteries. You see here on the left, basically, the GaN gate charge characteristics and the difference that we have versus silicon carbide MOSFETs, which is the orange one, and versus silicon superjunction MOSFET, which is the gray one in this graph. What we can understand here is that the pink one, so the purple one, that is the gallium nitride, has the lowest gate charge characteristics and values, which of course also means here that we're going to have the lowest switching and gate drive losses with this technology. On the right, we have already mentioned basically the linearity of this capacitor is also the lowest output capacitor in terms of the absolute value, will enable us also for lower switching losses as well as easier zero voltage switching conditions. Now, moving to the last but not least, of course, here application is the inverter when it comes to the automotive application. Of course, we can understand that here the efficiency is of a key role, and together with that, of course, also how much range actually an electrified car in this case would be able to achieve. And of course, to that, another key aspect is the cost optimization of such devices. As we mentioned as well, is the system design that we need to keep into consideration. For example, we need to be able to support 400 volt battery system designs as well as 800 volt system designs. And one key aspect also of that, as you can see here on the bottom right, is that for higher voltage ratings, we can also enable new topologies, the so-called multi-level topologies, that can enable higher efficiencies when it comes to higher battery voltages. Now, to show some actual topologies that are being used today, what we see here in the 400-volt battery systems is basically a very simple two-level B6 inverter. And I think this is today really the industry standard that we have. Also, from what you see from the semiconductor aspect here, it's quite simple. And with that, of course, it's quite simple to control. Moving to 800-volt battery systems, we see again here the two-level B6 inverter, which again is a quite simple. And in this case, the only difference between the 400 and 800-volt system is that here we're going to need 1200-volt capable power switches. However, with that, what we can also see, because of the motors as well that need to be used for such battery voltages, is that we're going to have more harmonic losses in the motors. And how can this be overcome? As we see here, we can achieve motor loss reduction by moving into three-level topologies. And you see here some examples on the right. So, for example, a three-level active neutral point clamp topology that is really achieving the best efficiency when it comes to our powertrain. Of course, with that, as you also see from the picture, we have a higher BOM count when it comes to the semiconductors. Of course, also the complexity that comes with that, but also the cost with that. This one, now, if we compare it to a three type, as we see here on the right, which is also being used in such applications, we see here that the vertical leg is now using 1200-volt devices, whereas the horizontal one is using, for example, in this case, 650-volt gallium nitride devices. Also to mention here that in this picture, we're showing two individual switches, but don't forget that we can always replace this with one GaN bidirectional switch. This topology allows for a very good trade-off between the performance and the cost, while also being a bit easier to implement versus the active neutral point clamp. Of course, here the efficiency will not be as good as the ANPC topology. Now, for this application, we also need to understand the different load profiles that are very important and very relevant to how we design the powertrain in this case. So what you see here is a bit of a mapping of the torque versus also the speed versus also the current that the inverter needs to enable for such a powertrain. One key aspect that we need to take into considerations and how autos are designed today is the peak power demand, which is basically the vehicle performance is mainly described by the top speed, the maximum acceleration, and also the hill hold capabilities of the car itself. This means that the drivetrain needs to be designed in a way that also the power semiconductors will be able to carry also very high currents while remaining in their safe operating area throughout the operation of such inverter. Another aspect that we need to take into consideration is the partial load demand. So basically is a load profile that doesn't require the maximum current capability or maximum speed or maximum torque, and is also the one that is mostly frequently used in our everyday driving if we would have an electric car. So basically, this one is also very relevant to actually how the WLPT measurements are done and how also the range should be measured of a car itself. In this case, what we need to do, as you can see, is we need to design the drivetrain in such a way where we also enable the highest light load efficiency versus the previous point where we have very high currents. Why is this now important? What we see here is an example for a 400-volt battery systems comparing the different solutions that we have. So what we can see here, we see that the silicon-based solutions versus a fusion of silicon and silicon carbide, which I'm going to explain actually what this is, versus silicon carbide and GaN, how can we enable with this latest Wide-Bandgap based topologies a higher efficiency and a higher range or a higher battery saving when it comes to this application? And we can see here that with the fusion technology of silicon carbide, we can achieve plus 3% versus the normal silicon solution. whereas with the silicon carbide, we can achieve around 3.5 to 4%, or with the gallium nitride around 4 to 4.5% in terms of gain. Here as well to mention that, as you can see, there are two different switching frequencies. So what is mainly used today is 10 kilohertz, but also moving to higher switching frequencies will give an additional benefit for silicon carbide and gallium nitride topologies. Now, you may be wondering what is the silicon MOSFET and also silicon fusion, right? So you see here on the right a bit of the explanation that we can have in terms of configurations of today's cars. So we can see basically that we can have in a car a rear inverter in the rear axle and one in the front axle. And what we are basically doing, we're splitting these two inverters using either silicon carbide or silicon solutions in the configuration 1 and 2. Now, why is this done? Is of course because the silicon carbide can enable lower switching and conduction losses when it comes to light load conditions, whereas the IGBTs, for example, can really enable low conduction losses when it comes to very high currents. So we really here are trying to optimize the design. This is one approach. And another approach, of course, here is that, as you can see on the configuration 3 and 4 in this case, is to have in the same inverter, so in a common inverter, both solutions possible. And this is also what we as Infineon have developed actually for the first time in the market, the so-called silicon carbide MOSFET and IGBT fusion module. So really what we're trying to do here is to put in a single module both technologies, so both silicon carbide and IGBT technologies, and really extract the best out of these two based on the final load profile that the inverter needs to achieve. Another example, now moving to the 800 volt battery systems, as we can see here, is how the different topologies also can enable a further range or battery saving. So moving from a silicon to a silicon and silicon carbide to only silicon carbide to these type inverters that we have seen also in the introduction of this chapter, we can understand that here there is a lot of benefit to gain basically when it comes to additional range. So we see, for example, that the full silicon carbide solution can achieve around 6.5% more range versus the standard silicon solution. And the T-type can achieve up to 11% actually versus the silicon solution. This is, as you can see also here from the topologies themselves, really enabled by using either, for example, a B6 with 1200 volt CoolSiC MOSFETs, or a T-type sort of topology using here 650 volt GaN devices in the vertical leg, or in the horizontal leg, I'm sorry, or 1200 volt CoolSiC designs in the vertical leg itself. So also out of this picture, I think is very clear how new technologies like silicon carbide and gallium nitride can really enable efficiency gains when it comes to the whole system. So not only from the inverter, but also to the motor side. And also, of course, with that to lead into more range that is, of course, important for this application. So we have covered everything for today. So I just want to summarize basically what we have seen and what are the key points of the wide-bandgap technologies. What we have seen is that the wide-bandgap semiconductors are really here supporting the future of electrification, but also of decarbonization that comes with that by taking advantage of the unique material properties that we shared in the introduction of this presentation. And going into more now specifics, what we have seen is that with wide-bandgap, we can achieve higher breakdown voltage, which means that we can either move into simpler topologies or we can enable further innovation when it comes to such topologies in the different applications. Another key aspect, especially for example when it comes to GaN, is that we can enable higher switching frequency designs, and of course with that also a higher power density and more compact final design in these applications. Another key aspect as well is the lower switching and conduction losses that wide-bandgap like gallium nitride and silicon carbide can achieve. That also would give us then a higher system efficiency, which is also very important for all applications today. Another key aspect as well is the superior thermal conductivity that in this case, for example, silicon carbide has, which means that we can have higher temperatures, but also designs in harsher environmental conditions. But also when it comes to the packaging that we also saw, for example, dual side cooled concepts that comes with the technology, we can also have improved cooling concepts in the final designs. So now also to close a bit the presentations, because before we go to the Q&A section, I wanted to mention that we as Infineon are also hosting a very much wide bandgap focused developer forum every year. And in this case, as you can see, it will be taking place in the 11th of March. Is a completely free to register virtual conference. I have also left the link here for the ones that are interested. So please feel free to learn more about this event, also to see the agenda, and also then to register yourselves for more news and more in-depth presentations regarding the wide bandgap technologies.
Fantastic.
Thank you.
Thank you so much for that, Alexandros. That was a really interesting discussion. I know that I personally learned an awful lot. We do have a few questions from the audience, and I would like to invite anyone to drop further questions into the Q&A tab you can see at the top right of your screen. But first of all, what would you say are the main challenges in the widespread adoption of these WBG devices?
The main challenging. So thanks for the question. What we have seen from this presentation, right? So we tried, of course, to focus on the benefits of the wide bandgap in the different designs. Of course, with that, I take an example, the active neutral point clamp topology that we have seen. Then complexity, of course, of such of these topologies come as well. And with that, also the control algorithm complexity is going higher, which means also that there is a sort of software related complexity that the customers need to take into consideration while, for example, trying out new and innovative topologies. So I think also the software and the control algorithms here need to be taken into consideration when it comes to implementing gallium nitride. Another challenge, of course, I would say here is the long-lasting, of course, experience that we have in the silicon-derived technologies, and also, of course, with that, the manufacturability that we have with that, right? So I take an example. We all know today that since a lot of years, silicon technologies are being manufactured on 300 millimeter wafers, or 12-inch wafers, whereas GaN and silicon carbide at the moment are sort of stuck, let's go like this, at 6-inch, at 8-inch. This is one aspect, of course, when it comes to volume production. The other aspect is also the improvement that we still need to do in the manufacturing of these technologies, just because they're newer technologies. So there is also going to be a further improvement when it comes to the manufacturing. I think that's the main aspects. Maybe also one last aspect, of course, is also the cost that comes with that. And we also saw that the silicon in a lot of applications will still remain the main technology because also of this cost performance.
Is unfortunately always a bit of an issue. Now, you did just touch upon this a little bit, but how would you compare the long-term reliability of these different options? So one might be better for right now, but 5 years down the road, which one would have been a better choice? What's the difference in the long-term reliability?
Another great question. So I think what we also need to understand, and this also comes a bit into play with the, let's say, years of experience that we have on silicon versus silicon carbide and gallium nitride, is also all the quality related aspects that come with that. And I also want to mention here that we have also, based on the YEDEC standards, they are being standards developed where basically we are trying to correlate the physics that are behind, and also how actually the devices, the physical structure is being used for silicon carbide and gallium nitride, to understand what I would say are the failure mechanisms behind this, or also what are the sensitive points specifically to silicon carbide and gallium nitride. And with that, basically to map the relevant quality checks that we need to have in place in our front ends, but also in our backends, to make sure that we have a long-term reliability when it comes to such devices. So I think that's one of the keyest aspects here when it comes to long-term reliability. the years of experience, of course, that we have. And another aspect maybe to mention specifically for the JEDEC in this case is that we have a committee, which is called, by the way, for the ones interested, at least JC70, where also we as Infineon, our experts, are taking part. And what this standard, so the JC70 standard, was defined specifically for wide bandgap devices, so silicon carbide and gallium nitride, to basically create this quality related aspect and tests that need to be in place to really safeguard the reliability of these technologies.
And leading on from that question about long-term reliability, do you ever foresee these new solutions completely replacing the silicon ones in the future? Or do you think that we'll always see a mix of the two technologies working side by side?
Another great question. So I think it has been mentioned also in maybe in my previous answers to the previous questions, but also in the presentation itself. I think it's important that we as Infineon, we are really, let's say, major fans, I would say, of all three technologies, right? So, and this is why we are also developing and we're still developing and enhancing silicon as well as silicon carbide and gallium nitride, because we do really think that each application, based on the requirements that they have, they will have a sweet spot basically for each of these technologies. And I take an example now in this specific case, the silicon. We have seen that there are some applications that either because they require higher breakdown voltages. So, for example, the ones that IGBT we have today, or the modules that we have in railways, for example, or also applications like more consumer-related applications that are very cost-driven, will still remain, I would say, in the near future with the silicon technology. So I think the key message is really to understand that yes, we have new technologies, wide bandgap, but silicon is still being also developed, and we still believe that a lot of applications will make use of this technology.
Great, that's fantastic. If there are no more questions from the audience, I'd like to thank everyone for joining today. We had a great turnout, which was wonderful. This session will be available on demand. So if you're only able to catch part of it, or you think it might be of interest for a colleague, it will be available. I would like to once again thank Alexandros so much for sharing his time and his expertise with us this afternoon, and invite everyone to join another session at the fantastic Future of Electrification event from the lobby, which you can access just by clicking at the top left of your screen. So once again, thank you everyone, and we will see you in the next session.